This is the next video on normal distribution. So in this video, I'm going to talk about how we can use the normal distribution curve and the normal CD function on our calculator to give us an approximate probability for something which we could normally calculate with our binomial CD function. So we are approximating probabilities associated with the binomial distribution using our normal distribution. Okay, so this goes back to the time before the magic calculator, when we used to have to use the tables to calculate binomial probabilities. The table of values, the ones that you've got in the booklet, in the back of the booklet, go up to where n equals 50. When n was more than 50, we were unable to work it out properly because the tables didn't go that far and we didn't have a magic calculator. So what we used to have to do is we used to have to approximate or estimate what the binomial distribution probability would be using our normal distribution tables. And despite the fact that you don't need to do this anymore, because you've got your magic calculator, because it's such a nice bit of maths, they've left it on the spec, so for you to enjoy. So I'm going to talk about how we would do it. We're still going to use our calculator, but we're going to go through the process of applying the normal distribution to the binomial distribution. Okay, so it says, if a binomial distribution is given as x squiggle b with a number of trials n and a probability of success p, it says in some cases we can use a normal distribution to approximate probabilities for a binomial distribution. So we can't always do it. There are certain circumstances in which it would be okay and suitable to use this approximation. Here's a binomial distribution diagram. Okay, so you've seen plenty of these now. This is for 15 trials and the probability of success is 0.2. Okay, you can see the sort of general shape. If I sort of trace over the top of this, it's quite what we call skewed. So there's a lot, the higher probabilities are for the lower number of outcomes, and then it sort of tails off. Okay, so that's called skewed. If I show you another one, here's another probability distribution. Okay, this is still binomial, so it's still discrete data. This time we've got n is 100 and p is 0.5. So for n being 100 and p being close to 0.5, well, it is 0.5, what we end up with is a symmetrical probability distribution. The heights of the bars are still binomial, so there's still gaps between the bars. Okay, the height of the bars are still representing the probabilities. But it looks symmetrical as opposed to that one, which was skewed. Okay, so because when n is large and when p is a half or close to a half, what we end up with is what looks like a normal distribution curve, even though officially it's a discrete binomial distribution. When those two circumstances or those conditions are satisfied, then we will get a binomial probability distribution that looks symmetrical. And those two conditions allow us then to approximate using the normal distribution. So just to clarify, the conditions that we can approximate the binomial with the normal, n must be large, so we're talking more than 50, and p must be close to 0.5. Okay, so it's usually, you'll see questions where this is somewhere between 0.4 and 0.6. Okay, the bigger n is, the closer p is to 0.5, the more accurate the approximation. Okay, so those two conditions must be satisfied, and in exams they might ask you about why would it be suitable to use the normal approximation, and it'll be because of those two conditions that have been met. Okay, so how do we do it? So the first thing is the parameters are different. So when you have a binomial distribution, you know the number of trials n, and you know the probability of success p. When you're using the normal distribution, you need to know the population mean and the variance, or the standard deviation. Okay, so how can we use the normal distribution CD function on our calculator if we've got number of trials and probability of success? Well, what we do is we can convert. So if we are given the binomial distribution parameters, we can convert them into normal parameters using these two rules. So we're told that mu is NP. So to get the mean, we can multiply the number of trials by the probability of success. And then the variance, sigma squared, is NP 1 minus P. Okay. Now you do get them in the formula booklet, I'll show you in a second. Okay, but that's how we convert from binomial parameters into normal parameters. And just to show you why that is, a little diagram at the bottom here. So we've got a little curve. Okay. Binomially. So it says x is binomially distributed with 50 trials. So that's n. And then probability of success, that's n, and that's your p. Okay. So we've got n and p. And those are the blue little lines there. Because n is big, because it's 50, because probability of success is close to a half, then those blue lines, that probability distribution, looks pretty symmetrical. Okay. Over the top of that is a black curve. That black curve is the normal distribution curve. And the normal distribution curve has got a mean of 24 and a variance of 12.48. So that 24 is the product of 50 and 0.48. So that's the NP. The 12.48, which is the variance, is the 50 times 0.48 times 1 minus 0.48, which is 0.52. And you get the variance. Okay, sigma being the square root of that, which is about 3.5-ish. Okay, if you look at the diagram, you can see that it's symmetrical. If I put the mean in there, it's symmetrical about 24. Okay, so that NP, that 50 times 0.48, is where that curve is symmetrical about. And we also know that 5 standard deviations that way, so 5 lots of 3.5-ish that way, and 5 lots of 3.5-ish that way, 100% of that population will sit. So all those probabilities will add up to one whole one. Okay, so that's how it works. So if you are given binomial distribution information, then as long as the conditions are satisfied, then we can convert the parameters into normal distribution parameters. Okay, just to point out, they are in the formula booklet on page 8. Okay, so they are mentioned there. There they are. It doesn't explicitly say what it's for. It just says it's for distributions, but there they are. So it might be just worth in your formula booklet just writing down that that is what it's for, and then you don't forget. Okay, so those two things are for converting binomial to normal. Right, so just going to do one question, and then we need to talk about something else. So it says a biased coin has probability of head of 0.53. Okay, so that's our p-value. Change colour, don't like writing in black. That's our p-value, and the coin is tossed 100 times. And the number of heads x is recorded. Write down a binomial model for x. So we just need to define our parameters. So x is distributed binomially with 100 trials. Ugh. Go away. 100 trials, and the probability of success is 0.53. Okay, it says explain why x can be approximated with a normal distribution, y, etc. Okay, and so that is just asking you about, are the conditions met? And yes, they are. So n is large, it's 100, and p is close to 0.5. Okay, both conditions are satisfied, so therefore it can be approximated using the normal. And then it says find the values of mu and sigma in this approximation. Okay, so mu is NP. So to get mu, pen's not working properly. To get mu, we're going to do 100, which is n, times by 0.53. So mu is 53. And then for sigma, well, sigma squared is np 1 minus p. So 100 times 0.53 times 0.47. So the variance is going to be, well, the standard deviation is going to be the square root of all of that. So 53 times 0.47, which is 4.99 to 3 sig figs. Okay, so that's how to, excuse me, that's how to convert from binomial parameters into normal parameters. Okay, and then you would use that mean and that standard deviation. So then we would say y is normally distributed with mean of 53, standard deviation of 4.99, and then we would then use those sets of values to make our approximation. Okay, so that's the first part, converting the parameters. Okay, before we can do any calculation, there's something else that we need to consider. We need to consider the fact that the binomial distribution is a discrete probability distribution where the height of the bars represent the probabilities, and a normal distribution is a continuous distribution where their area represents the probability. So how can we work out an area when we've got gaps between the bars? Well, what we do is we plug the gaps, and we do what we call a continuity correction. So it's a bit like turning a bar chart into a histogram. Okay, the bars have to be close together. So think about when you did stats and you had class boundaries where you had to plug the gaps. It's a little bit like that sort of principle. Okay, so here we've got some discrete bars or sticks, as I like to call them, okay, what we can do is we can plug the gaps. So let's say we wanted to work out the probability that x is greater than or equal to 6. If we were doing this with a binomial distribution, we would add up, or your calculator would add up all the heights of all those where x is greater than or equal to 6, and that would be the answer. Okay, the normal distribution needs an area. So what we need to do is we need to make those sticks turn into bars and plug the gap. So on the next slide, that's what it's going to look like. So you can see now that those sticks, the black lines, the black sticks, have been filled with bars. So it's like the sticks have expanded out and expanded until they've turned into bars, and all those gaps have been plugged. Now if you look now, the blue shaded ones where I had probability that x is greater than or equal to 6, actually that 6 now starts there at 5.5. So what we would actually do is we would say, after we've converted to get our normal distribution, y is greater than 5.5. So that's called a continuity correction. And there it is on the next slide. Okay, so you can see all those, that's the cut-off point there, which has gone down to 5.5. So the sticks have expanded and turned into bars that are touching each other, so that all those gaps have been filled. And that's called a continuity correction. Okay, I'll show you some more. So here, let's look at this one here, x equals 9, which is this one here. Okay, it says, if you want to work out the probability that x equals 9, okay, so on your binomial calculator, you would use binomial PD, and you would essentially be working out, if I just draw a stick there, there's that stick at 9, and that would be your discrete value, okay? But because that bar has had to plug the gaps, then we've actually got a continuity correction of that one line at 9 has actually expanded and gone down to 8.5 and up to 9.5. Okay, it's often easier to do it if you draw some sticks. X is less than or equal to 3. Well, if I draw a stick at 3 and another stick at 2 and another stick at 1 and another stick at 0. Okay, so that's what binomial is saying. If I make those sticks go fat, so I'm going to turn them into bars, red bars, like that, then actually that value there is now the cut-off point. And that's why the continuity correction is y is less than 3.5. I'll show you some more. Okay, so let's say we wanted to work out with the binomial, x is less than 4. So less than 4, well, if this is a binomial, so the x is representing the binomial value. Okay, remember x binomial is discrete, so less than 4 actually means 3, starting at 3, then going down to 2, then going down to 1, and then going down to 0. Okay, so that's what you would do if you were doing binomial. Imagine those sticks now getting fat. So we're going to plug the gaps, plug those gaps. Then that point there will be the cut-off point, and that will be less than 3.5. Greater than or equal to 9. Well, greater than or equal to 9 includes 9. So that'd be 9, and then 10, and then 11, etc. upwards. Okay, so 9's the important one. If that stick gets fat, so we plug those gaps, etc., then that point there is going to be the cut-off point. That's the key point, and that is at 8.5. So the continuity correction is greater than 8.5. If I do x equals 6, well, that's just 6. So there's your stick at 6. That bar, that stick is going to get fat and turned into a bar. So your cut-off point is going to be there and there. So that's going to be 5.5 to 6.5. Greater than 8. Well, the first whole number greater than 8 is 9. So we want 9, 10, 11 onwards, etc. So actually, in terms of diagram, it's going to be the same as the top one. Okay, those sticks are going to get fat. 9 will go down to 8.5. So that's going to be y is greater than 8.5. Okay, let's look at the next one. X is greater than or equal to 7, but less than 10. So if I do, including 7, 8, but less than 10. So we've only actually got 7, 8, and 9. If those sticks get fat, like that, then that's going to be our cut-off point, and that's going to be our cut-off point. So it's going to go y will be greater than 6.5, which is here, up to 9.5. And then the last one, greater than 2 but less than or equal to 5. Well, greater than 2 does not include 2, so that's 3, 4, 5. And then if those sticks get fat, then cut-off points are going to be 2.5 and 5.5. Okay, so those are continuity corrections. It's worth practicing those. I wouldn't try and use any weird formula to help you because you just won't memorise it. The best thing to do is just consider what I've just done in terms of what numbers would you actually want, what whole numbers would you actually want, and then imagine those sticks getting fat, or do a little diagram to help you like I did. Right, let's put it into practice. Because what is all this? It all will become apparent when we do a question. Right, it says, the binomial random variable has got a number of trials 150, which is large. So it's got a large n, and it's got a probability of success close to 0.5. And it says it's approximated by the normal random variable, where the mean is 72 and the standard deviation is 6.12. Okay, so that is n times p, and that is n times p times 1 minus p. So it's already been converted for us. If that hadn't been done, then we would have to do that ourselves. Okay, usually in an exam, you would have to do that yourself, so you'd have to remember to do that. Okay, use this approximation to find the probability that x is less than or equal to 70. Okay, now what you could do is you could do, you could use binomial CD with n is 150 and P is 0.48 and X is 70. And you could work out on your magic calculator, because you got it, what the actual answer is, what the actual probability is. And maybe later it'll be worth having a look to see how close it is. Okay, but what we want to do is we want to use the normal distribution to approximate. Okay, now that X equals 70, that X is relating to the binomial. What we need is a question, a probability to work out where we've got a Y value. So we need to do our continuity correction. I'm just going to call that CC. So this is where the fat sticks comes in. So instead of X is less than 70, less or equal to 70, we want the probability of Y is less than. So if we think now, we've got 70, 69, 68, etc. downwards. Okay, if that stick gets fat, those sticks get fat to plug the gap, then that's going to be the cut-off point there, which is 70.5. Okay, so instead of using the binomial, we're going to approximate it now using those numbers, and that number. So we actually want to work out from our normal distribution curve, where the mean is 72, the probability of getting less than 70.5. So you can use the normal CD function on your calculator. 70.5 is going to be your upper limit, and then you can just put 0 in for your lower limit. Okay, and you should find that that is 0.403. Okay, if you work it out using binomial CD, I'm pretty sure it's like 1,000th off in terms of how accurate it is. Okay, probability that X is greater than 80 but less than 90. So if we do the continuity correction, that means that Y, so inclusive of 80, which means we need a stick at 80, and then that's going to go up to, but not including 90, so it's going to go up to 89. And then those sticks are going to get fat. So the cut-off point is going to be there and down to there. So we want, actually, the continuity correction between 79.5 and between 89.5. So that's your continuity correction. So we want, from our normal CD, that's 72, and we want that little bit of area whereby that's 79.5 and that's 89.5. Okay, so you can get that from your normal CD function, and you should get an answer of 0.108. Okay, just going to do one more example. Okay, it says a drill bit manufacturer claims that 52% is, one second. Okay, a drill bit manufacturer claims that 52% of its bits last longer than 40. A random sample of 30 bits is taken and X lasts longer than 40 hours. Okay, so we've got 52%, so that's our probability of success, and we've got N is 30. So X is distributed binomially with N is 30 and P is 0.52. Okay. Find the probability that X is less than 17. Okay, it doesn't say anything about approximating. So we're just going to do this with normal CD, okay, because N is not large, so we couldn't get a decent approximation, and it doesn't tell us to do an approximation with this question. So we're just going to use binomial CD. Okay, so to get less than 17, then using binomial CD, we actually need to do less than or equal to 16. Okay, so this is using binomial CD. Okay, so you should get, for that, when you stick it in your calculator, 0.628 to 3 sig figs. Okay, then it says a second random sample of 600 drill bits. This is now a large value for N, is taken using a suitable approximation. Okay, so it doesn't specify a normal approximation, but you're only going to ever do one approximation. So if it ever says a suitable approximation, that's what it means. Use the normal distribution. Find the probability that between 300 and 350 bits inclusive lasts longer than 40. So we're after the probability that X is greater than or equal to 300, but less than or equal to 350. Okay, so we've got our binomial parameters, and we've got the question that it wants us to work out. Okay, sorry, actually no, that's not right. Those are no longer our binomial parameters. I'm going to say X is now binomially distributed with 600 trials and 0.52. So we're going to use 600. So we've got our parameters and we've got our question. Okay, in order to use a suitable approximation, we need to 1, change our parameters, and then 2, do our continuity corrections. So I'm going to change the parameters first. So if X is binomially distributed, then Y will be normally distributed. So I'm just changing letter. Okay, so we're going to do 600 times 0.52 to get the mean, which is 312. And then to get the variance, we're going to do 600 times 0.52 times 0.48, and that's going to give us 149.76. So I've now got my 2 parameters. Okay, and then the second thing I need to do is my continuity correction. So if I'm including 300 and 350 and those sticks then expand, 300 is going to go down to 299.5 and 350 is going to go up to 350.5. Okay, so I've now got my continuity correction and my normal parameters. I can now work out that probability by just considering that area. So there's my curve. I want 312 between 299 and 350. So I'm after that area there. Okay, don't forget your standard deviation is the square root of 149.76. So if you stick that in your calculator, normal CD, then you should get an approximate probability of 0.846 to 3 sig figs. Okay, if you actually work out this using the binomial CD function, so the bit that I've highlighted, then you should get, it should be almost identical, because N is so large and P is so close to 0.5 that I should imagine it'll be, you'll get 0.846 to 3 sig figs. Okay, there's a question that I've not done about flower bulbs on page 20, and there's a question on page 21 for you to have a go at. If you get the opportunity, then ask your teacher to check your answers for you, or use the work solutions. Okay, that's the end of the video.